There, ladies and gentlemen, this is Stan Forster, your instructor. I'm getting some questions on M3A4 about how to proceed. And so I thought I'd try to give you a few hints, even work part of the problem for you so that you can proceed. Okay, so this is our circuit diagram. We have a 10-volt power source battery and a 10-volt power source battery. Okay, and I realize I just drew those wrong in the document I wrote up. Okay, but you know, they're marks on the paper. Okay, so we'll just go for it. Anyways, we have this seemingly very complex circuit diagram here, and we're going to just use our rules to make it a little simpler, step by step, work backwards, see if we can find out what the equivalent resistance is for the entire circuit, and then figure out what the current through is, and then step back one by one, and so we can figure out what the current is. If we can figure out what the current through this whole loop is, we can figure out what the current then is, what portion of the current goes to this 10 ohm resistor and how much goes to the 7 and the 3 ohm resistors. Okay, and as you might know, okay, 10 and 7 plus 3 is equal to 10. So you might guess that if they're equally hard to get through, whatever current is actually passing through this bottom conductor here is going to be split evenly between the two. So that's an idea. Okay, now let's take a look at this top one here. Again, we see resistors in parallel, but oh, this is all very complicated, isn't it? So one of the things at the very end we're going to do is I'm going to kind of come over here. Okay, if you're doing the lab at the same time, you're already familiar with the University of Colorado and their physics education and training simulations. And so I went ahead and I built the circuit. We're going to test, we're going to make our calculations, we're going to test it all out. And then we're going to come back here and we're going to see whether or not the work works. Oh, good Lord, did I actually just say that? Okay, so let's go ahead and start off here. Here's our circuit. Okay, yeah, if you were to draw this and hand it in, and I would say no, please go back and retype it. I imagine, though, if you're needing some help at this point, you want the help more than you want neatly typeset solutions. So let's go for it. All right, here's our circuit, and again, here's the things I drew backwards. I just realized I drew those backwards. Okay, please be, I'm not going to go back and redo this. I want to get this out to you guys so that you can get the help you need. All right, so this is a 10-volt battery. This is a 10-volt battery. It's convenient to assign a reference voltage, 0 volts, right between them. So if we go from 0 volts through a 10-volt power source, then we know that this is going to be 10 volts. If we go backwards through a 10-volt power source, God, I really hate that. Okay, it's going to be minus 10 volts. So this is minus 10 volts here. This is plus 0 volts plus 10 volts. Conceptually, let's take a look at this. We're going to treat this as though these are two separate circuits. But this conductor right here in the center, we're going to treat it as a 2-lane highway. Right? So the current is going to go through this 5 ohm resistor and down, and it's going to get split at this junction through the 10 ohm and everything else. It's going to pass through the 7 ohm resistor, it gets split here, go through this 10 ohm and the 7 ohm and the 3 ohm, and they're all going to combine and come back here. That's conceptually, that's what we're going to do. Down here in the lower one, we're going to imagine all this current coming up through here, going the other direction. So like a 2-lane highway. So the net current is going to be different here, 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 but by the time we get to this particular portion, all the current flowing in this direction is going to be. Okay, so we have this 10-volt power supply, current coming through here. Let's take a look at this. This 7 ohms and this 3 ohms, these are in series. They're going to add up. This is 10 ohms and 10 ohms. 10 ohms in parallel with 10 ohms. Okay. How do you add parallel resistors? 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. Do the math. So 1 over 10 plus 1 over 10 is 2 over 10. That's equal to 1 over the equivalent resistance. Flip the whole thing over, both sides. The equivalent resistance is equal to 10 over 2, or 5 ohms. This whole circuit network can be replaced with an equivalent resistor of 5 ohms. We have 10 volts, 5 ohms. Use Ohm's law. Voltage, potential equals current times resistance. So if the resistance is 5, we need the current to be 2 amps in order to satisfy Ohm's law. In other words, The current at this point here, coming into this junction, is 2 amps. The current coming out at this point here is 2 amps. Now, 7 plus 3 is 10, so 10 and 10 in parallel. It doesn't take much. The upper circuit, we're treating it as completely separate. Remember, this here is all at 0 volts or ground. So we have R1, 2, 3, 4, 5, and 6. It's 5, 7. Let's go 75. Okay, 7 ohms, 10, 10, and 3. All right. What are the kinds of things that we can do? We can recognize that these are R3 and R6. These are in series. It's going to add up to 10. So we've got a 7 in series with a parallel 10 and 10. And that's exactly what we've done here. Circuit diagram 2, simplified circuit diagram 2. So we have 10, 10. No, this is R sub 3, 6. Just lets me know that I've combined R3 and R6. So 7. Well, what happens when we put two 10s in parallel? This is going to be equal to 5. But it's going to be 7 in series with a 5. 7 in series with a 5 is going to give us a 12. Okay? Because we have to add the 7 on the 5 is going to give us 12. Now we have a 10 in parallel with a 12. Just go ahead and add those up. 1 over the equivalent resistance is equal to 1 over 10 plus 1 over 12 equals, and let's keep going. Okay, it's going to come out to be 60 over 11. Okay, and it's like 10.45454545. Just keeps on repeating. Okay, and I'm gonna hang on to all the digits I've got for right now, and then we can round to the appropriate number of digits when we're done. All right, but right now we're just going to let the calculator rip. Okay, so we have this 60 over 11 ohms plus 5 ohms. Okay, because again they're in series, so it's 10 point. Oh, I'm sorry. This is 60 over 11 plus 5 is 10.45. 45. Okay. Going to use Ohm's law. Potential is equal to current times resistance. If we solve for resistance, we find that the current passing through this power supply is 0.9565. Again, as many digits as the calculator is going to give you. Okay. Now we know then that the current passing through R1 is this here. Would we care what the current passing through this is? No, we don't care, because that's not even actually a real resistor. It's an equivalent resistance, okay? And it's going to be this first current anyway. So let's figure out what I1 is. We figured out. Oh, I'm sorry. We figured out what I1 is. But let's take a step back. We have 10 in parallel with the 12. Remember, we had that back up here. 10 and 12. So we're taking a step backwards. So we know that this 0.9565, whatever, okay, that current coming into this junction is going to be split between a current going through resistor 4 and a resistor going through we're going to say whatever goes through that 12. So basically whatever goes through the 10 here is, whatever's left is going to go through the rest of the circuit. I'm going to apply the loop law. Voltage change through the battery plus the voltage change through resistor 1 plus the voltage change through resistor 4 right there is equal to 0. So 10 minus, I should have probably just VB there, okay, minus R1 I1, which is resistance 1 current 1, minus resistance 4 current 4 is equal to 0. All the potential you gain here has to be equal to all the potential you drop here and you drop here. Now, the current passing through this 5 ohm resistor is not the same as passing through this 10 ohm resistor. The current passing through here is the sum of I4 and the whatever passes through the rest of the circuit. Okay, so we have current 1, but we don't have current 4. But once we've plugged all these numbers in, we can see that we have only one unknown. We solved for that unknown. We probably should have solved for it up here. All right. Solve for it up here. We come out with 0.52173. Okay. Originally I came up with 5.2, and then I realized I'd forgotten to divide by 10. So, there's a little sanity check there. Just look at that. Does that make sense? You got your total current is here. Wouldn't make sense to say that you split this in two and one of them is actually 5 amps. Okay, so that would not make sense. Anyways, okay, so 0.54. Look at this junction here. Here's the 5, 10, and 12. We noted that the stuff coming in is 0.9 something amps. This is 0.5 amps. This is going to be like 0.4 something amps. And here it is again with, and I left off the amps. Okay, 0.411. Okay. And does that make sense that, 5 plus 4, 0.5 plus 0.4 is about 0.9? Yeah, that makes sense. Okay. We're going to take another step back. Okay, remember, what were we at here? What was this, circuit 4? We're going to take a step back all the way to circuit 2. All right, so we know what the current is through here. We know the current coming through here, okay, through the rest of those circuits is 7, resistor 5, and resistor 3, 6. Okay, now resistor 3 and 6 are 7 and 3, so we know that whatever current I36 is going to be the same for this resistor and that resistor. Okay, we'll have to figure out what the voltage drops are separately, but we'll be able to figure that out. Okay, so we know that coming through here is 0.4161, however many digits we've got. We know that these two resistors, this resistor that's actually in the diagram and this equivalent resistance, I36, the 7 and the 3, are both equal to 10 ohms. Convince yourself that because it's equally hard to get through both branches of this, that the current is going to be split. So I didn't actually do the math. I just hit divide by 2. Okay, and so these are going to be, the total resistance coming into this junction is 0.41 and it's the current passing through resistor 2. So we figured out the current, the voltage drop across resistor 2. You're going to use that current and that resistance. But going through this branch and that branch, that's your current. Okay. Now that gives you enough right there to be able to figure out what the voltage drop is across every resistor in this network. You can figure out what the current is through every resistor in this network. And you can probably also figure out some funky ways of figuring out what the current is at this point and this point. Let me see. Let me come back all the way up here. What the current is at this point and that point and that point. And whether or not you have a net flow from one battery to the other. So let's see if we can't go back and see what that circuit diagram looks like. Okay, so we've reproduced 2 10 volts, 5, 7, 7, 3, 10, 10, 3, 10, 7, and 3. All right, so let's see what we can do. I think one of our first predictions is that the current, once it reaches this point up here, it's going to be 2 amps. And indeed, it is 2 amps. Okay, the current through here is going to be 2 amps because, the current, electrons are conserved. You can't get rid of electrons. So if they're coming in this way, they got to come out this way. Now, another of our predictions was that the current passing through this branch and this branch is 1 amp. Again, it's 1 amp and 1 amp. Okay. So how much current is, now we don't know what the current, okay, we can take a look here and we can see if we thought about it a little bit, we'd say, yeah, okay, so we've got one battery and another battery. These are actually in series, so they're going to actually drive current through this. There's going to be some small net current that comes up this way, but it's also, we didn't know whether it's going to come back this way or not. Because we got this 2 here and a 2 amp here, but these are, the analysis we did would have these small amounts of currents going this way, so these are going to be smaller. But let's see if we can figure out how much current is put out by this 10 volt battery to the rest of this network. And it was like 0.9 something, 0.96. Okay, how much goes from here to there? Did we come up with something? 0.52. Why is it more than half? Because if you look at all this stuff here, is there going to be more resistance here than here? Is this easier to go through? And it turns out that indeed yes, because if we, again, once we did all the analysis, this ended up being 12 ohms. And so this current here is going to be 0.43. Let's see if we can go here. And this is 0.22 and 0.22. And then when you add all these up, we're going to see that if you wanted to, and this is not in the problem, but this is 4.0, 1.04, and then once this comes through, in our analysis, we have it going back this way, but it would be current this way plus a 2 amp that way. Turns out to be that this is still positive in this direction, so 1.57, and then this one here combines with that one, and 1.78, and then we add another 2.2 to it, and we get back up to 2 amps. Okay, that's we're at 20 minutes now, so many of you have probably signed off already, but I hope that gets you started, and I'm going to get this fired off to you. Okay, bye.